Hello, welcome to Modern Atomic Theory again. Today we're talking about quantum numbers, and I'm sure you're really anxious to hear about what those are since we've been talking so much about quantization lately. Quantum numbers simply describe the orbitals of an electron, and there are 4 of them. The first quantum number is the principal quantum number. Imagine that. The principal quantum number determines the energy state that the electron is occupying. So they are numbers like 1, 2, 3, 4, and the higher the number, the greater the energy. So that's what the principal quantum number is. Sometimes it's represented, the letter N equals 1, 2, 3, or 4, or whatever the energy state is. The second quantum number is the azimuthal quantum number. You don't have to remember that big long name. It simply determines the shape. And the shape will be designated by an S, a P, a D, or an F. The S looks like this. The shape of the P orbital looks like this. And the combination of these right here images give us the D orbital, and these are the F. So those are the shapes. They're shape orbitals. They determine what shape it is. The third quantum number is the magnetic quantum number, and due to its complexity, we're not going to really discuss that much. It determines the spatial orientation. The fourth quantum number is the spin quantum number, and lo and behold, it determines the spin. So it was discovered that electrons have a particular rotation on their axis, and they are able to rotate in 2 different directions. And in order to clarify that a little bit on paper and make it easy for us to understand, this was sort of adopted as the way we show spin, either up or down. There can only be 2 choices. So we have a little arrow up or a little arrow down to designate what spin it is. And it takes all 4 quantum numbers to determine the state of an electron in an atom. So every single one of these quantum numbers is needed to determine the state of an electron. And no 2 electrons can have the same 4 quantum numbers in the same atom, ever. That is not allowed. It never happens. So if, for example, an electron was in the 1s orbital, and it was spinning this particular direction, up, another electron could not come into that orbital, the 1s orbital, and spin up. It was an impossibility. It would have to spin down. So here's a designated s orbital. They're calling it a 1s here in this picture. This orbital is allowed to have 2 electrons in it. Those 2 electrons have to have opposite spins. So no more than 2 electrons can occupy an orbital at the same time, and if 2 electrons occupy that orbital, they must have 1 spin up and 1 spin down. So this is part of the Pauli exclusion principle. So it's just named Pauli exclusion principle because a man by the last name of Pauli discovered this special characteristic, and it's just an important one to remember because no 2 electrons could have the same 4 quantum numbers. Now, here is just an interesting thing to note. This is a 1s orbital. Here's a 2s, just a drawing, a representation of what a 2s orbital might look like. Here's a 3s orbital. And you notice that the principal quantum number in each of those orbitals is different. Each of them are an s orbital, but this is in 1 principal quantum number, this is a 2 principal quantum number, this is a 3 principal quantum number. I actually didn't write the 2 here, but you'll notice that with the increase in energy state, that probability that you'd find the electron there, it gets farther and farther away from the nucleus. So that's just an interesting fact to note, that the increase in that principal quantum number takes the electron farther away from the nucleus. So how many electrons can each shape orbital hold? So if we have this shape here, this s orbital, right there. At the s orbital, here's the number of sublevels in each orbital shape. It only has one. It doesn't have any more sublevels. So the question would be, how many electrons could fit in that s orbital? And I want you to just think about that for a minute. See if you can come up with the answer. It's 2. 2 electrons, one spinning up and one spinning down, can fit in that s orbital. Now, what about the p orbital here? Okay, it has 3 sublevels. Each of those sublevels could hold 2 electrons. So, how many electrons could a p orbital actually hold? The maximum number would be 6. The maximum number for d electrons, or for a d orbital, would be 10 because it has 5 sublevels. And for an f, it has 7 sublevels, so it could hold a maximum of 14. That is the very, very most number of electrons that these different shapes could hold, the s, p, d, and f. So the sublevels could also hold 1 electron, and the sublevels could also be empty. They don't have to have any electrons in them at all. But if they do have the maximum number, these are the maximum numbers that each one of these can hold. Does the shape of an orbital affect or describe the movement of the electron? Absolutely no. The shape of the orbital only indicates the probability that the electron will be in that space. So, say, for example, this s orbital. The electron is not going around in a circle or doing things like this. This shape only is an indication of, based on the probability density, that the electron will be have a high probability of being found right here, and they will have less probability of being found here. Same with these p orbitals. The electron does not orbit like this or move like that or anything. It's really their probability density clouds right here. There are higher chances of an electron being found in those denser locations than somewhere else. So that is what the shape of the orbital means, not that the electron will move a certain way. It simply means that there is it indicates the probability that the electron will be found in that space. And one more thing, all atoms possess all orbitals, even if they aren't full. So if this is, say, a hydrogen, and this is the 1s orbital that the one electron in hydrogen occupies, that hydrogen atom also possesses a 2s orbital and a 3s orbital. It possesses p orbitals in outer principal quantum number shells, and it possesses all of them, because if that electron is absorbing energy, then it's going to bounce out to these other outer shells, and they actually exist. So that's another concept just to keep in mind. So hopefully you will all have a chance to see this and come to class and be ready to learn a little bit more about writing electron configurations now that you know all about quantum numbers. So thanks. We'll see you later.